If you've ever had to seal a crack in concrete, you know what a pain it can be, and how quickly those cracks spread. But what if concrete could heal itself? Just like skin? Well, that's not science fiction anymore. Research teams in the Netherlands, Sweden, Denmark, and the US are reinventing one of the world's most widely used materials. Each team has found a way to make concrete come alive. It all started in the Netherlands, at TU Delft University, where microbiologist Henk Jonkers created the world's first bioconcrete. He mixed regular cement with tiny bacterial spores and their food source, then sealed them inside little pellets. When water seeps into a crack, those bacteria wake up, eat their food, and start producing limestone, filling the gaps as if nothing ever happened. As Jonkers explained, water is the culprit for concrete, but it's also the key to healing it. These bacteria were actually discovered in extreme soda lakes in Russia and Egypt, where they can survive for years in high pH conditions. This Dutch invention was the first true self-repairing concrete, a game changer for bridges, tunnels, and buildings. This invention marked the birth of self-healing concrete, durable, low maintenance, and climate smart. Nearly 8 years after the Dutch experiment, in northern Sweden, a more advanced and evolved version of the same concept emerged. In a cold weather lab, researchers engineered a new type of biocement that literally regenerates its own cracks. In Stockholm, Swedish civil engineers took it further. They created a concrete that repairs itself using living bacteria. The bacteria feed on calcium lactate and excrete limestone, sealing the crack within days. The key player is Bacillus pseudofermis, a hardy bacterium that thrives in alkaline environments like concrete. They designed a material that wakes up when exposed to moisture and air. When water seeps in, it activates, multiplies, and bonds the minerals back to the original surface, closing the gap permanently. Tests show it can heal cracks up to 0.8 millimeters wide in under 3 weeks, fully restoring its watertight seal, even in freezing Arctic conditions. Engineers estimate structures made from this living concrete could last over 200 years, dramatically reducing maintenance and waste. Sweden is now testing it on highways, tunnels, and flood barriers, with EU funding pilot projects across Europe. This isn't just repair, it's adaptation. Concrete made not just to endure, but to survive. For more than a century, the technology behind making concrete and cement has remained largely the same. However, the process of producing cement is far from eco-friendly. According to Eureka Alert, cement manufacturing is responsible for about 6% of global CO2 emissions, and the material continues to release even more emissions as it cures into concrete. In a study published in the journal Matter, researchers at the University of Colorado unveiled a remarkable innovation, a living concrete that not only grows, but can also regenerate. The team created a scaffold made of sand and hydrogel, into which they introduced specially selected bacteria. The hydrogel provided moisture and nutrients, allowing the microbes to proliferate and begin mineralizing, much like the natural process that forms seashells and coral reefs. The result was a solid, durable structure with a strength comparable to traditional cement. But unlike conventional materials, this new bioconcrete possesses a truly extraordinary ability. It can regrow. When researchers cut a parent brick in half and added more sand and hydrogel, the bacteria activated again, creating 2 new bricks. In fact, one single brick could reproduce itself up to 8 times over 3 generations. This breakthrough opened the door to a revolutionary concept, building materials that can heal, adapt, and even reproduce. Building on this biological inspiration, another American research group, this time at the University of Nebraska-Lincoln, took the idea even further. In a study published in Materials Today Communications, Dr. Congrui Grace Jin and her team developed a self-healing concrete system inspired by lichens, resilient symbiotic organisms made of fungi and photosynthetic bacteria that thrive in extreme environments. Their design combines the fungus Trichoderma ricea with cyanobacteria such as Anabaena inequalis and Nostoc punctiform. Once embedded into concrete, these microorganisms need only light, air, and a trace of moisture to activate the self-repair process. Unlike previous bacterial concretes that required added nutrients or chemical agents, this new approach is fully autonomous, relying entirely on natural environmental resources. Laboratory results showed that it maintained its healing capacity even in dry, alkaline conditions typical of real concrete structures, achieving up to 80% higher healing efficiency than earlier systems, while producing no harmful byproducts. Beyond its environmental advantages, this living concrete could also play a role in space construction. Because it relies primarily on sunlight and minimal resources, Dr. Jin's team envisions using it for building sustainable habitats on the Moon or Mars. Working with researchers at Texas A&M University, they are now exploring the social, ethical, and legal implications of deploying living materials in infrastructure. If successfully scaled, this innovation could dramatically reduce maintenance costs, extend the lifespan of bridges and buildings, and redefine the very concept of what it means for a material to be alive. And then came Denmark, taking things one step further. Engineers at DTU have developed something even more radical, a concrete that doesn't emit CO2, it absorbs it. Made with marine bacteria, crushed seashells, and seawater, this living concrete hardens through biological mineralization, just like coral reefs. No fossil fuels, no chemical heating. It actually grows stronger over time, and after just 21 days, it outperformed traditional cement in strength tests. The process is carbon negative, locking CO2 inside its structure instead of releasing it. Danish teams are working with the US startup Biomason to scale the technology for coastal cities and seawalls. This could redefine how we build, cleaner, stronger, and sustainable from the start. The result? A carbon-negative, renewable building material that's stronger and more durable than traditional cement. It's already being tested in seawalls, coastal walkways, and low-rise buildings, and could cut the construction industry's emissions drastically. These breakthroughs show a future where concrete could be self-healing, carbon-neutral, or even carbon-negative, repairing itself while helping the planet. Sure, right now, bioconcrete is a bit more expensive and not as strong as regular concrete, but the possibilities? Absolutely incredible. Living concrete isn't just science, it has measurable impact. It cuts maintenance by 25% and CO2 emissions by 15% since fewer repairs are needed. 1,500 new green jobs were created worldwide in 2025 through bioconstruction projects. A tunnel in Berlin saved around 100,000 euros annually, reducing repair downtime by 40%. A seawall in Sydney self-healed after storms, protecting 5,000 homes. Scaling to 100 cities could save $1 billion a year. By 2050, with 70% of humanity in cities, living concrete could become the backbone of climate-resilient infrastructure. If 10% of global concrete adopts this technology by 2040, we could cut 2 million tons of CO2 annually. Imagine cities that heal themselves after earthquakes, storms, or just daily wear and tears. Like any new tech, it's not perfect. At this stage, bioconcrete isn't a quick profit play, but it might be one of the smartest long-term investments in the future of construction. Right now, bioconcrete is still in its early stages. Production happens mostly in labs or small pilot facilities, and the cost is still significantly higher, in some cases several times more, than conventional concrete. The main challenges are biological, keeping the bacteria alive long enough, making sure it performs well in different climates, and scaling production efficiently. So no, it's not yet ready to replace every bag of Portland cement, but that's exactly why it's interesting for early investors. The opportunity isn't in selling the concrete itself. It's in owning the technology. Startups like Biomason, Green Basilisk, and divisions of BASF and Lafarge Holcim are racing to patent new bioformulas. These companies are actively seeking strategic partners, research funding, and infrastructure investors. Getting involved early, through venture capital, green funds, or R&D partnerships, means being part of a market that could redefine how we build. Looking ahead, some analysts suggest that advanced regenerative and self-healing materials might capture a meaningful share of sustainable construction, though exact figures are speculative. As cities push toward net zero, and as life cycle cost and maintenance become ever more important, materials that can reduce degradation, repair themselves, and extend infrastructure lifespan will be in demand. So while this isn't a short-term return game, for an early adopter with the right risk tolerance and long horizon, investing in bioconcrete could be worth it. Bioconcrete isn't just a new product, it's part of a larger shift toward regenerative infrastructure. Cities and buildings that maintain and heal themselves. If you're looking for short-term returns, this isn't it. But if you're thinking like an early adopter, like those who believed in solar energy or electric vehicles before they became mainstream, then yes, investing in bioconcrete could be worth it. But with $500 million invested in research and development in 2025, momentum is growing fast. Northwestern University researchers have developed a carbon-negative building material that could make concrete and cement much more sustainable. By using seawater, electricity, and CO2, they can grow minerals like calcium carbonate and magnesium hydroxide, which act as carbon sinks while also being usable in concrete, cement, plaster, or paint. The process works a bit like how coral forms shells. Electricity splits water into ions, CO2 is bubbled through, and the ions react to form solid minerals. These minerals can even be customized in size, shape, and density depending on how the process is controlled. 1 ton of this material can store over half a ton of CO2, all without weakening the concrete. The vision is to set up modular reactors near shorelines, capturing CO2 from nearby plants and turning it into building materials that lock carbon in permanently, creating a truly circular and eco-friendly construction approach. If nature can heal, why shouldn't our cities? These living materials remind us that progress doesn't have to mean separation from nature, it can mean working with it. If you like this video and learned something new, make sure to leave a like, subscribe, and share it with someone who loves discovering how nature and science come together. Because the future isn't just being built, it's growing.